Hello. For our project, for our group project, our group decided to do the Spinpossible topic, and our group members are Felix, Joshua, Justin, and me, Steven. So, what is Spinpossible? Spinpossible is a game that you play on a 3x3 board, and it has tiles from 1 through 9 randomized on this board, and each tile will either be right side up or upside down. And basically, the objective of this game is to convert the randomized tiles to an ordered tile of 1 through 9 with every tile right side up. And you're also supposed to try to solve this randomized board using the least amount of possible spins to get the completed board. Each spin that you do also will rotate by 180 degrees. So this is what the actual board looks like. On the left, we have a randomized board with numbers 1 through 9, some right side up, some upside down, and then on the right, we have a completed board ordered 1 through 9, everything up, right side up. So now we will look at how many spins it actually takes to complete the board we had just seen. So if we start with the board right here on the left, we see that we spin the first two right columns, 180-degree rotation. That's the first step. And now we spin the middle column, a 180-degree rotation. That leaves us with just spinning the 1 and 2 tiles, 180-degree rotation. And now we have a completed solved board in only 3 steps. So how does Spinpossible relate to group theory? Well, let's consider the 3x3 board as a group G consisting of K elements. The group will consist of 6 spin types for a total of 36 different spins. So group G consists of the spins, as we see there, 1 by 1, 1 by 2, 2 by 2, 1 by 3, 2 by 3, and 3 by 3. So using the elements that we found in the group G, we will go over the generation of a set, closure, associativity, the identity, inverse, and commutativity.
Here we have the general case where the board would consist of an m by n tile, and each tile may be oriented right side up or upside down. The position of the board are fixed locations and numbered from m to n, starting at the top left and proceeding left to right, top to bottom. A rectangle is a selection of rows or columns. The rectangle is R composed of m and n, denotes the position where m is on the left corner and the position that n is in is on the right corner. Given a rectangle R, we can then denote the spin of R by spin R, or which is equal to spin m composed of n. So a spin will rotate a row and or column by 180 degrees, and we agreed to have it clockwise. So every element of spin, m composed of n, can be expressed as a product of at most 3mn minus m plus n. In this Spinpossible's 3x3 board, spin 3x3 is the group generated by all possible spins of the 3x3 board. The group operation is a composition of spins. Every element in the 3x3 can be expressed as a product of spins. Every product of spins yields a board that is then scrambled. Every scrambled board is determined by the product of the spins. We can see a 1-1 correspondence between elements of the spin on the 3x3 and scrambled boards. So if we let K be an element of the 3x3 board, where K is to the -1 power, this will return a scrambled board and can also return to the solved board or the original. Finding a solution to a scrambled board is equivalent to finding the minimal steps, K to the -1 power. Now, the generation of a set, as we have previously established when we defined a 3 by 3 as the product of generated by the collection of spins on the 3 by 3 board. We can say that a spin will generate some position on the 3 by 3 board. We can also refer to a set of spins as generating a set on the 3 by 3 board. Overall, we can say that every net action from the 3 by 3 board corresponds to a word consisting of spins. Therefore, we can see that there's closure or composition of two net actions on a 3 by 3 board and results in a net action in spins on the 3 by 3 board. This means that the 3 by 3 board is closed under the composition of spins.
All right, now we're going to talk about associativity. If we recall an idea from group theory, the composition of function with compatible domains and codomains is associative. That is, if f, g, and h are functions with compatible domains and codomains, then f star g star h is equal to f star g star h, as you can see on the slide. Since composition of spins is just a function composition, then we can say the composition of spins is also associative. Also, since the spins generate spin 3 by 3, the composition of net actions for spin 3 by 3 is associative. Therefore, the composition of net actions from spin 3 by 3 is associative. Okay, so now we're going to move on to the identity. Using a standard n by n board, we can find the identity element. First, define the rectangle RMN on an n by n board. Next, we can take the rectangle MN and apply the appropriate spin MN, to show the following. Now, applying spin MN again, we get the following. We can see that applying the operation spin MN twice to our rectangle MN will result in us getting back to where we started. In other words, spin MN times spin MN is equivalent to doing nothing. In both the general case and in the 3 by 3 case, there is an identity element whose corresponding net action is do nothing.
Hello, I'm Joshua Johnson, and I will begin talking to you about inverses and Spinpossible. As you can see on this slide, I demonstrate inverses. I pulled these pictures from the Congregate version of Spinpossible. On the first picture, my cursor selects the 1 and drags down to the upside down 6. This is known as spin 1, 8. After I let it go, the spin is performed, and the resultant square is the second picture. I drag my cursor again from the 6 to the upside down 1. This once again is known as spin 1, 8. The result is shown on the third picture, which is the same board as the first picture, showing the inverse is itself. If we think of every spin as a symmetry rotation of 180 degrees, it becomes clear that a rotation of 360 degrees would be needed for the identity. So in order to create the inverse, we must spin whatever rotation we've done twice. That means for every A that is an element of spin 3 by 3, A star A will equal I, the identity. Or in other words, A is equal to A inverse. This is important for the game itself because if we look at the inverses of a composition of spins, the inverse would be just the reverse order of the inverses composed. This is also helpful because if you know how the board was scrambled, then you can solve the board by just inputting the inverse. It's important to note that every element of spin 3 by 3 has an inverse and therefore meets that group criteria. Now let's take a look at commutativity. Can we compose any two words in any order and still get the same resultant? Well, it turns out that the next slide it is possible to show a simple counterexample to show that it is not commutative because of the qualifier word any. Therefore, we say that spin 3 by 3 is not in general commutative. Any words may or may not be commutative. Simply put, spin 3 by 3 is not a commutative group. And here's an example of two words that are not commutative. Let's consider the word spin 1, 8 and spin 2, 3 composed with spin 1, 4. And spin 1, 4 composed with spin 1, 8 composed with spin 2, 3. These words are composed with the same elements that do not have the same ordering. On the picture on the right, I go through each composition, and it becomes evident that the resulting grids are not the same, so therefore is not commutative. This does not mean that all the words are not commutative, only that the property does not hold as a group. To summarize, we found that spin 3x3 is an example of a group. It meets the criteria of closure, associativity, identity, and inverse. The group is cyclic, meaning that it has a generator, but it is not an abelian group because there are some words that are not commutative in spin 3x3. And I just wanted to say thank you for listening to our presentation, and I think you guys should give this game a try. It was actually quite fun.